Hello students and friends. Today's tutorial is about the property of light that explains why rainbow colors are produced in soap bubbles. Why is the feather of a male peacock looks so vibrant with its changing colors? This color formation in several other animals is due to light interference. But what is interference? Interference pertains to any situation in which two or more waves overlap in space. And the principle that explains this overlapping of waves is known as the superposition principle. This is the basis of the experiment done by Thomas Young, known as the Young's double-slit experiment. In his experiment, Young used two slits as coherent sources of light. Coherent here means that the two waves have the same frequency with constant phase relation, but not necessarily in phase to each other. In Young's double-slit experiment, the waves coming from the slits interfere constructively or destructively, depending on the difference in distances between the slits and the screen, as shown in the diagram. Supposing we have here two slits, S1 and S2, and the waves will be entering these two slits and they are going to overlap or interfere at this point where there is a screen. So, because of this overlapping or addition of the two waves, there is what we call constructive interference that will happen. And the result is, you will see here a very bright band or bright fringe. Okay, it is exactly at the center of the screen. Now, this happens because the difference in the path for S1, let's say the path is L1, and for S2, the path is L2, and they are equal, so there is no path difference. It is zero, right? Which suggests that there is a constructive interference occurring, and this is captured by the screen where a very bright spot or a very bright band is formed. Now, this is not the only fringe or bright fringe that is seen on the screen, but there will be alternating bright, dark fringes. Okay. Uh, for the second bright fringe, okay, this is illustrated in this next diagram. Supposing the difference in the paths of L1 and L2 is an integral multiple of lambda or wavelength lambda, all right? So uh, the kind of fringe that is produced on the screen is also a bright fringe. But that is the result of the constructive interference occurring, okay, at that point. Below the bright or central bright fringe, there may also be exactly the same bright fringe, okay? In other words, above and below the central bright fringe, there will be exactly the same alternating bright fringes. All right. Now, for instances when the path difference is an integral multiple of 1 half lambda, okay, 1 half lambda, the point where the, shall we say, the uh, out of phase of one wave overlaps with an in phase, okay? wave, then there will be what we call destructive interference, some kind of cancellation. All right, the cancellation of the two waves, because an in phase and an out of phase waves will simply cancel out each other according to the principle of superposition. And as a result, we see a dark fringe or a dark band. Okay, so the path difference will determine whether uh, the interference is will result to a bright band or a dark band. This is explained further in the next slide. All right, so as we said earlier, as the waves interfere, they produce fringes. All right, so this is an example of uh, the dark, bright, dark pattern that is seen on the screen. All right, we said that if the path difference L2 minus L1 is a multiple of an integral multiple of lambda, and that's expressed in this simple equation, path difference is equal to m times lambda, where m stands for uh, the multiple integral. Say, for example, if m equals 0, all right, there will be no path difference, and that pertains to this central bright band, denoted by m is equal to 0. But if m is positive 1, then we are talking about the first bright band above the central bright band. All right, and so on. Okay, until probably up to the third, fourth, or fifth bright band. Okay, as I said earlier, there will also be the same exactly identical bright bands. Okay, to the right of the central bright band or below, depending on how you are describing the position of your screen. All right, that's why we have here positive or plus minus 1, plus minus 2, and so on. So the formation of bright bands is examples of what we call constructive interference. Now, for the destructive interference effects, which result to dark regions or dark fringes, okay, the formula for path difference is equal to m plus a multiple 1/2 lambda. All right. So again, m is equal to integer 0, positive or negative 1, positive, negative 2, and so on. But there is an additional 1/2. All right. And the result will be an integral multiple of 1/2 lambda. That is the first dark band that will be seen. That is the closest bright band to the central bright band, or the closest dark band, I should say, to the central bright band. Okay, if m equals 1, okay, if m equals 1, then we are talking about 3 halves. Okay, an integral of 3 halves lambda. If m is equal to 2, then we are talking about 5 halves, okay, lambda, and so on and so forth. The wavelength lambda of light that is formed as bright band in Young's double-slit experiment is found to be related to the distance between slits D. The distance between slits and screen, denoted by capital L, and the distance between adjacent bright or dark bands, represented by X. So we have this very important formula or equation. Lambda is equal to X times D divided by L. Okay, notice again that L refers to how far the two slits, okay, are from the screen, and small d refers to the separation distance between the two slits, while x refers to the distance between two adjacent bright bands or two adjacent dark bands. Okay, this is the formula that we are going to apply in our next questions or problems. We are also interested in determining the angle that locates the nth order bright fringe, which is given by this equation: sine theta is equal to m lambda divided by d. And for the angle that locates the mth dark fringe, the formula is sine theta is equal to m plus 1/2 quantity lambda over d. Okay? The angle theta refers to this angle here in the diagram. Here's our first sample problem. In Young's double slit experiment, the distance between the slits is 0.20 millimeters. Alright, that pertains to this distance here. The distance between the slits and the screen is 1.0 meter. That is labeled here as L. It is found that the separation between the successive dark fringes is 2.9 millimeters. That pertains to X. Question. Letter A. What is the wavelength of the light? Letter B. If the separation of the slits is doubled, so if D is doubled, what happens to the distance between successive fringes? Alright, so X, notice that the X that is being referred to in the question is the distance between adjacent, alright, between successive or adjacent dark fringes. So we will see the solution to this problem in the next slide. Alright, so once again, let us recap what the problem number 1 is asking us to determine. So in the diagram, we have the distance of the screen from the two slits, which is denoted by L. So this quantity is given, and the separation distance between the two slits is also given, and the distance between the two adjacent or successive dark fringes is also given. And we are looking for the wavelength lambda of the light, okay, that is used in this experiment. Okay. Here we have the summary of the given data. First question, letter A, is looking for the lambda wavelength of the light. And then letter B, we will answer the question, what would happen to the distance between the adjacent dark fringes if the distance of separation between the two slits is doubled. So for our first question, letter A, we just use the formula lambda is equal to x times d divided by L. And substituting, okay, just be careful that in using this formula, all quantities have to be expressed in the same unit. And I decided to use meter as our unit for all the quantities. For example, x here is originally, x is given in millimeter. So when converted to meter, that is 2.9 raised to the negative 3 meters. And for the distance d, originally it is 0.20 millimeter. So in meters, that is equal to 2.0 times 10 to the negative 4 meters, all over L, which is already expressed in meter, 1.0 meter. All right. So when you multiply these two values and then divide it by the value for L, we will get this value for the wavelength lambda, 5.8 raised to the negative 7 meters, which when expressed in a more commonly used unit for wavelengths of light, it is equal to 580 nanometers, because in 1 nanometer we have 10 raised to the negative 9 meters. All right. And This wavelength 580 nanometers actually corresponds to the wavelength of the yellow light. So we use yellow light, a monochromatic, okay, source of light in this experiment. Okay. Question letter B. How do you find, or what will happen to the value of x, okay, the distance between the adjacent dark fringes, if we are going to double the separation distance between the two slits? All right, so our formula becomes x is equal to L lambda over D. From the original formula, lambda is equal to x times D over L. Okay, we just transpose x to one side of the equation, and you will notice that x is just inversely proportional to D if L and lambda are held constant. So which means that if the distance between the two slits is doubled, okay, the effect is that the value for x will be half, okay, or will just be one half of its original value, meaning that the two the two fringes, dark fringes, will get closer to each other. All right, this is our second sample problem. If 500 nanometer and 650 nanometer lights illuminates two slits that are separated by 0.50 millimeters, how far apart are the second order maxima for these two wavelengths on a screen that is 2 meters away? All right, so let us identify the given data. We say that there are two, what we call, sources of light, each having a specific wavelength. The first lambda, lambda 1, is 500 nanometer, and the second lambda is 650 nanometers. All right. So these two waves will enter the two slits. All right, whose separation distance is 0.50 millimeter. Now, there's a screen 2 meters away. All right, and we are asked, okay, we are asked to determine the distance between, okay, how far apart are the second order maxima. Maxima here refers to the bright band, all right, of the second order. In other words, m is equal to 2, all right. We are talking about the second bright band closest to the central bright band. But since there are two wavelengths or two waves that uh, considered in this experiment, naturally there will also be two kinds of bands, okay, corresponding to 500 nanometer and 650 nanometer uh, light waves. And that's exactly what we are going to determine. How far are the two maxima or the two bright bands, both in the second order maxima? And we denote that by delta x, since we're talking about the difference between the distance of these two bright bands. All right. We have our value for the integer capital M, which is equal to 2. Uh, we can actually determine the value of x. All right, the value of x for each type of wavelength using the original formula that we used in the previous problems. But since these two waves will be having the same what we call separation distance between the two slits. They have a common value for D. They have a common value for L. All right, and they are both pertaining to the second order maxima. So what we can do instead to make it shorter is to combine them, and we will just subtract the two wavelengths lambda 2 minus lambda 1, and then the corresponding value for x will now become the difference in the value of x, or delta x. All right, so that is the shortcut formula that we can use here. When we substitute, of course, we get the difference between the two wavelengths already expressed in meters. 650 times 10 to the negative 9 meters minus 500 times 10 to the negative 9 meters to be multiplied by the distance of the screen from the two slits, which is 2 meters. Then all over the value for capital M, which is 2, and then multiplied by the separation distance of the two slits expressed already in meter, 5 times 10 to the negative 4 meter. And doing our arithmetic, we will get a value for delta x equals 0.3 times raised to the negative 3 meters, or in millimeters, that is 0.3 millimeters. So this is the first, or the question that is being asked in the problem: how far apart are the second order maxima, okay, for the two wavelengths on the screen 2 meters away. This is now our last question, number 3. In Young's experiment, okay, double slit experiment, the source is a sodium lamp emitting yellow light, whose wavelength is 589 nanometers. The separation of the slits is 0.20 millimeters, and the screen is 2 meters from the slits. Calculate the angular positions of the second and third maxima. What is their separation on the screen? So as usual, we identify the given data. Lambda is equal to 589 nanometers. The separation distance between the two slits is 0.20 mm. And the value of L, that is how far the screen is from the two slits, 2 meters. We are required to find the angles theta 2 as well as theta 3. Okay? And also delta x, meaning when seen on the screen, all right, how far apart are the two fringes? Again, we use the term second and third order maxima. Maxima is the term used for bright bands. Okay, the second bright band and the third bright band. How far apart are they? As seen on the screen, that is the meaning of delta x. So we will first calculate for the first angle theta 2 using the formula. Theta 2 is equal to the inverse of sine, okay, m lambda over d, or arc sine of m lambda over d. Substituting, okay, m is equal to 2, lambda is 589 raised to the negative 9 meter, and the value for d is 2.0 times 10 to the negative 4 meters. And using your cycle, you will get the value of 0.34 degrees. Okay, a pretty small value for theta expressed in degrees, theta 2. Then let's move on to determining theta 3. Theta 3 using the same formula. Okay, and substituting, we have arc sine of 3 because we are talking about the third maxima, okay, multiplied by the wavelength again and divide by the same value for separation distance d. So again, using your cycle, we will get the angle theta 3 equals 0.51 degrees. All right. So these are the answers to the first question, calculating the angular position of the second and third maxima. And finally, to calculate for delta x, we use the formula delta x is equal to lambda 2, all right, times L divided by MD. All right. And of course, that is what we will get when we substitute the value for lambda and the value for L, all expressed in meters. Okay. The separation distance means how far apart are the two bright fringes, second and third maxima. So you will notice that our value for capital M, this is capital M, okay? Our value for M in determining the delta X is just equal to 1, all right? Because the two bright fringes are adjacent to each other. When we say second and third maxima, all right, we are just talking about uh, the difference between those two adjacent, take note of the word adjacent or successive bright bands. So that requires us to use the value for capital M equals 1. Okay? But their corresponding X, all right? The corresponding X that can be computed will now become uh, the separation distance of the two bright bands. I hope that is clear. That's why I put here delta X. Okay, delta X. Again, this is a shortcut because we could have determined the value of X for each. All right, for each case, for the second order maximum, okay, we can determine the value of X. And then next, we can determine the value of X for the third maximum. But doing so, in doing so, since it's just a repeated procedure, okay, we might just as well use this delta X formula the same way that we followed in our earlier problem, all right, where we simply subtract the value of M when M is equal to 3, and then when M is equal to 2, what's the difference? It's equal to M equals 1, and that's what I use here as capital M. All right, I hope that makes sense. So our value for this separation distance of the two maxima will be equal to 5.9 times 10 to the negative 3 meters. So that will be all for today's tutorial. Thank you very much once again.